足元をご注意ください。
They took a couple of different approaches. They tried just multicasting the data. They tried using sort of anti-entropy techniques of replicating select data between servers, and none of this really cut it. What this led to was this sort of paper. So in 1989, Academic Algorithms for Replicated Database Maintenance. And this was part of the set out ways of managing this kind of replicated data, but using an academic firewall type approach. So in the paper, what they did was they looked at a couple of different methods, and they analyzed that kind of direct mail approach. So every time an email server received an email, they would forward it on to all of the other servers. But the problem with that was that some servers didn't know the locations of the other servers. Sometimes messages would get lost. It was relatively efficient, but it wasn't particularly reliable. And I mentioned anti-entropy before, but they took this anti-entropy approach. So in a regular time period, one of the servers would choose another one at random, and they'd sort of sync their databases. They tried to diff between their two data stores, and this proved pretty efficient. It was sort of very efficient in managing to kind of get this data replicated across systems.
は右側です。少々お願いいたします。ご参照お願いいたします。
proposes a solution for having this distributed member list, or a cluster. One of the kind of the key reasons why we need SWIM, we need something, is node failure. One of the kind of key things about SWIM is that we need to understand node failure. And the sort of the traditional approach to heartbeating, it just doesn't work. It's just not reliable. They often fail because you've got things like network load, you end up with hotspots and a sort of a central server, and this leads to false positives. And in sort of a cluster membership, false positives is something we really, really want to avoid. Now, on those false positives, I want you to remember that last point, because we're going to have to come back to that in just a little while. Specifically, I want you to kind of take note of a phrase which is mentioned, which is process crashes. So, when the authors of SWIM, when they first looked at this kind of traditional heartbeating failure detection, they took those two kind of common approaches. So the method where a central server receives all of those heartbeat messages. And this is problematic, as I said, because you end up with this hotspot. If the central server fails, then you end up with a complete failure of your failure detection. And the other approach is the multicast approach. So you either use literal sort of network multicasting and send a message to every server, or you use a custom server approach to your multicast hotspot. In both of those instances, the core problem is that a multicast approach leads to high network load. And not only that, but it doesn't scale. You end up with sort of a quadratic increase. So every time you double the number of servers in a cluster, you're quadrupling the number of messages. So there needed to be a better way to sort of manage this. And with all that knowledge, Das and the others define these properties for SWIM. They state that there should be a constant load per message group, that process failure detected has to be in constant time, has to be consistent, and that there should be an infection style or gossip process for membership updates. evidence here that it's complex to implement, it's not necessarily proven, and it causes a high network overhead. So how does SWIM manage grave failure? So the SWIM paper goes on to describe an approach. And what it states is that rather than just marking a node as immediately failed, mark it as suspected. So we don't get any things back. So rather than gossiping that a node has failed, what I'm going to do is I'm going to gossip that I suspect node B is misfunctioning. And the benefit of kind of the suspicion approach is that any node can refute that allegation. And again, because we're using this gossip-based protocol, there's a very good chance that the node which is under suspicion is actually going to get the message and it's going to say, well, you suspect me to fail, but I haven't failed. And if you can then gossip the reputation, so you won't end up with this instance where you can get these flapping nodes. But there again are some limitations to SWIM, because the original paper mentions 55 nodes, and quite often we're operating at a much, much larger scale than 55 nodes. Certainly some of our users are running thousands and thousands of nodes. And we kind of flap this out, so from users taking the console running this massive scale, we kind of go back and say, well, we're getting this flapping, we end up with these situations where there's a large number of false positives being marked in the member list. So we looked at this, and Apache Corp research team has determined that there should be an extension to SWIM, which they call Lifeguard. So Lifeguard's a complete replacement of SWIM in it. It's just 3 applications, and 3 applications are usually dynamic fault detector timeouts. So we should have some awareness that maybe this, which is faulty. Suspicion of timeouts. So in the instance that we have suspicion, we should be able to and also reputation timeouts, we should be able to use those. Reputations timeouts are using that sort of fault detection. So it allows the node to assume that it's maybe fault. So also make these false suspicions. It can kind of take a little bit of reflection and say, maybe it's me that's broken. So when the node sends out a probe, so it doesn't receive a response, that's kind of its first step to start suspecting that it's a problem. You see, there's 2 situations in those nodes. One could be that the network as a whole is completely knackered, but probably it's the diagnose of having transient failure. And then when we get into that situation, choose standard suspicion. Even we could get an answer.
お出口は右側です。もう一度時間調整いたします。ご視聴ご視聴いたします。
One of the assisting nodes doesn't receive a probe. So, if G doesn't receive either an ACK or a NACK before the timeout, it can now safely assume that it has a fault and not the destination. And the algorithm works like this, so it allows us to tune up various different parameters. We can kind of say that for a failed probe, we're going to increase our counter by 1. With a missed NACK, we're going to increase by 1. If we have to refute a suspicion by 1. If we get a successful probe by 1. And the kind of the maximum node self-awareness is going to be 8. The beauty of this approach is that we're not tuning things on a global level, we're tuning things on a local level. So that even if a single node is misbehaving, the entire cluster isn't altering its behavior, and there's a very good chance that we're still going to be able to detect these failures. The second part is the kind of dynamic suspicion timeout. So with this, what we do is we start with a high suspicion, we give the system a chance to be able to refute the suspicion. But we kind of change it up, because what if I suspect a node is faulty, and you all are also telling me that that node is faulty? There's a very high likelihood that the node is actually faulty. So we start to reduce that sort of period before a node can transition between suspected and failed. And we use a logarithmic scale, so very simply, we kind of take the largest reduction for the first additional suspicion message is received, and we slowly start reducing those until we get to a minimum timeout. Part 3 is about enabling a node to ensure that it can actually refute a suspicion. Because the suspicions are kind of based by this gossip protocol, it's going to take a number of rounds before they're actually going to get that. So what we do is we say, well, let's implement this buddy system. So if I suspect a node that I'm about to probe is faulty, I'm going to let it know about it. So I'm going to piggyback the suspicion message with my ping. And that's going to give the opportunity for the node to be able to refute that suspicion. And then it's going to have a very gossip-based protocol. And the results of this have been pretty decent. I mean, we've seen 98% reduction in false positives. We've seen an 8% reduction in network traffic. There are some small kind of drawbacks. Yes, it takes 7% extra to be able to detect a failure, but based against the fact that you're getting a 90% reduction in false positives, we really think it's been worthwhile. In addition to kind of just doing this work and putting it into console, this is an academic piece of research that Apache Corp have done. So John Curry, our research director, has presented the paper Lifeguard at a number of academic conferences, and it's currently undergoing its academic defense. So it's kind of cool. And it's all open source. So the member list package, which is the foundation of the implementation of SWIM and Lifeguard, and it's used by Console and Nomad and all of HashiCorp's sort of distributed applications, is an open source Go package why I was motivated to join. And what I found, especially in the early years, a lot of the work that we did was around software delivery. So we go into client companies, work with client people to build software. And around in those days, because of the continuous delivery focus on new things and new ideas, a lot of companies were very interested in how do we do this. And the thing that I found, what I tended to be involved in, was working with the operations teams, infrastructure teams, because you're going to do continuous delivery of getting software into production very frequently. That means you have to involve end-to-end, this is DevOps, all of these things come together like this. What I found was that many teams, although they were using, maybe starting to use cloud computing and using infrastructure as code tools, like Chef and Ansible and these kinds of things, they weren't always finding the ways to use these best to get the most value out of these tools. And so that was what inspired me to write this book, Infrastructure as Code, where I took ideas that I'd been learning from people and seeing, and that we'd use on projects and tried to explain, like, here's where I feel like are good ways to do this. And so today we're talking about the evolving infrastructure, the ability to do that quickly. And so, because this is one of the main drivers, one of the things that companies are very focused on now is how can we move quickly, how can we adapt to the market. Even older companies are finding that they're worried about, so like in the banks